At the end of the first part of this video, I had pointed out that hydrogen and lithium and magnesium and beryllium and magnesium had the same Lewis dot structure. In fact, that's going to be the same across all of the groups in the S and the P block. Everything in group 1A has one valence electron. Everything in group 2A has two valence electrons, and so its Lewis dot structure always has two dots. We aren't going to do much with transition metals because they're just not very easy to predict. But if we go back across to the P block, then we have boron and aluminum with 3A, 3 valence electrons. We already did carbon in our last video. Carbon had 4 valence electrons, one on each side. Nitrogen, then, we would need to pair up one pair to get 5 valence electrons. We did oxygen in our last video. And fluorine, going all the way to 8. 8 is the configuration of our noble gases, the low energy stable state. So really, if you know the electron configurations across row 2, period 2, you know the electron configurations that you're ever going to need to know. Because if you know what lithium does, you know what sodium, potassium, rubidium, and cesium do. If you know what oxygen does, you can get sulfur and selenium and tellurium and polonium. Now, just talking a little bit about the transition metals. Part of the reason we can say that things like bromine and iodine have the same chemical properties as chlorine and fluorine is because a filled set of d orbitals acts very similar to filling up the p orbitals. A full set of electrons is stable and low energy. So as an example, we could look at something like zinc. Zinc is not going to make zinc 12 plus. If you're about to write down something like 12 plus, just don't. That would empty the entire 3d orbital and get me back to the farthest noble gas. However, that's not the valence shell. The valence shell is the farthest out electrons, and those are in the 4s. So in fact, zinc would lose its valence electrons, those 4s electrons, and form zinc 2 plus. It wouldn't break into that low energy full d subshell. Now, most of the time with transition metals, there are a few exceptions we'll ask you to know, but most of the time with transition metals, we won't be asking you to predict what ions are formed. We'll be figuring it out from other clues in a problem. So the last thing to look at is what happens if we have ions. Okay. Remember, we said that non-metals are the ones that will gain electrons. They will attract the electrons given away from metals. That's because we're trying to get to the noble gas configuration. Thus, if I look at something like fluorine, fluorine is element number 9. Well, the nearest noble gas is 10, neon. So the closest low energy state is the same number of electrons as neon, 10. That gives me the fluorine anion. I know it's a fluorine anion because fluorine always has 9 protons. No matter what happens to the electrons, the protons can't change. But I have 9 protons and 10 negative electrons. So I can think about it like a math problem. 9 minus 10 is negative 1. Or I can think about, what do I have extra of? I have extra negative electrons, so I have an extra negative charge that shows up. So in order to draw that, well, in this case, I would have 2s2, 2p6, isoelectronic, the same electrons as neon. That means I have 8 valence electrons on the F minus ion. So I would draw my F, and I'd go 1, 2, 3, 4, 5, 6, 7. That's fluorine. And now look, you can see that empty spot that I fill to make the fluorine ion. But I don't want someone to think that I think fluorine always has 8 electrons. So what I do is I put it in a bracket and I put the minus charge outside. Now, it doesn't matter to me whether you put 1 minus or minus 1, as long as you have that negative there. So let's try practicing this. I have 3 ions for you to try: sulfur, chlorine, and phosphorus. So what I'd like you to do is start by drawing the configuration for the neutral atom. Draw neutral sulfur, chlorine, and phosphorus, and then we'll look at how we can turn that into a full octet. So I'm going to pause for a minute, let you draw the neutral atoms, and then we'll fill in their octets to make the ions. So I've got sulfur, 6 valence electrons. You can see it doesn't really matter which way the electrons are drawn. I have 2 pairs and 2 singles, just like I did on oxygen, because sulfur is right underneath oxygen in column 6A. Chlorine here, I have 7 valence electrons, 3 pairs and 1 single. And phosphorus, I have 5 valence electrons because it is in group 5A. So I have 5 valence electrons, 1, 2, 3, 4, 5. Okay. So now I want to think, how many electrons do I have to add to get to a full octet? Well, if I look at sulfur, I have 1 spot at the top and 1 spot on the left where I have an unpaired electron. And so it seems like I can see here that I've got 6. I need to add 2 to get to 8, the octet. So I need to add 2 electrons to sulfur. I only need to add 1 electron to chlorine. It already had 7, so I just need to add 1 to get to 8. And if I look at phosphorus, I can see I have 5 electrons here. That means I need 3 to get to 8. But I can also see those 3 loner electrons there, so I can really visually see a spot to put 3 extra electrons. So what would that look like all filled in? Well, sulfur would have 8. To get to 8, I added 2 extra negatives. So that sulfur now has 18 electrons, but only 16 protons. It has an extra -2. Chlorine, I'm going to go ahead and add 1 electron to it, which is going to give me a -1 charge. And phosphorus, because I added 3 electrons, has now 3 extra electrons, or a 3- charge. Remember, when you add electrons, it forms a negative ion. I know that's a little bit counterintuitive. So when you do an anion, a negative ion, you should always end up with 8 dots, and the charge is however many electrons you needed to add to get to that 8 dots. For a cation, cations are going to be losing electrons. And so that means that cations are going to be made from metals. Metals lose electrons. Still trying to lose enough electrons to get to the nearest noble gas. So rubidium, which has the same Lewis dot structure as sodium and potassium and lithium and hydrogen, because it's in group 1A, it just has 1 dot. So you really kind of visually see, well, what would be easier, finding 7 more things to put in to get to 8, or just taking 1 away? So rubidium, which is 5s1, loses that 1 electron to get back to the configuration of krypton. And since we're losing an electron, you can actually kind of think about it just as erasing that dot. Well, when I form the rubidium cation, I actually take that dot away. And since I took away one electron, I have fewer electrons than protons now. And so now I have a positive charge. So rubidium is 1 plus. So because cations were taking electrons away, we conventionally just don't show the valence electrons that are left, because otherwise all of our anions and all of our cations would all have 8 dots all the time, and it would be harder to tell them apart. Since this is losing, we show that by literally losing the electrons in the valence shell and not having any electrons shown. So again, I've got some practice for you. So I've got magnesium, lithium, and aluminum. And we can start this by doing the same thing that we did before. Draw the neutral atom, and then we'll think about how many electrons we need to take away from these metals. So I give you a minute to draw them, and then we'll look at them. So you can pause it and draw them. All right, well, I have magnesium up here. Magnesium has 2 valence electrons, so it just gets 2 dots. Lithium, of course, has 1 valence electron. We did that before. And aluminum would have 3 valence electrons because it's in group 3A. So what I need to do is lose these valence electrons. And I can lose them literally just by erasing them and counting how many electrons did I have to erase. Because a cation, a metal, will not have any electrons in its ion structure. Are they really there? Yes. Are they there in the Lewis dot structure? No. So with magnesium, I would lose those 2 electrons. Since I lost 2, I have a 2 plus charge. With lithium, I lose that 1 dot, I get a +1 charge. And with aluminum, because I lost all 3 of those dots, I get a +3 charge. So with cations, you can look at how many electrons did I have to lose to get the charge on the ion.